Okay, we're continuing on talking about bonding. I think we got into chapter 12, and we talked about several different kind of types of bonding. Really, two sort of major types of bonding, and that is ionic bonding. And ionic bonding is always again between a metal and a non-metal, as we talked about before. Pretty much, if you see that combination. You should know it is going to be ionic. And because of those periodic trends we talked about, what we're going to see is again a transfer of electrons. And that's going to transfer from our metal to our non-metal. The result of that, again, is going to create a cation, which is positively charged, an anion, which is negatively charged. And again, is that electrostatic attraction that holds that apart. Again, no sharing of electrons here. Now, the other type of bonding is a covalent bond, and in a covalent bond, we basically between two nonmetals. And the deal with that again is because they are both nonmetals in this case, they both have pretty much the same type of periodic trends, which ultimately means that they both want to hang on to their electrons. And the best that they could kind of do is agree upon sharing. Now, as we also talked about, they will share electrons, but that sharing may be equal or unequal sharing of those electrons. So again, kind of equal or unequal sharing. But there is some aspect of sharing going on with a covalent bond. What helps us sort of determine, for example, whether or not those electrons will be shared equally or unequally is electronegativity, as we talked about at the end, I think. And electronegativity is the ability of an atom to bring electrons towards itself. And again, that increases on the periodic table as you go up to the right, decreases as you go down. Increases. Again, fluorine being our most electronegative element you could have. We talked about at the end there using differences in electronegativity to help us make that decision. You could calculate, as we did, the change in electronegativity values by basically looking at that table from Pauling and finding the two elements involved in that bond and due to difference in electronegativity. If somewhere between 0 to 0.4, it is considered a nonpolar covalent bond, which means we would expect the electrons to be shared equally. If it's really above zero point 0.4, so that's probably around zero point 0.5 to less than 2, it's going to be some type of polar bond. And usually above 2, but not 100% of the time, it's going to be ionic. As we talked about a number of times last time, you really don't need the difference in electronegativity values to determine ionic. Again, as soon as you can determine metal, non-metal, that's good enough. You really don't need the values. So really, for the most part, we'll use the values for maybe our non-metals and non-metals coming together to make a covalent bond. Also, a reminder that again, you sometimes don't even need the actual values to make a pretty educated guess in terms of polarity. So, for example, if we were comparing like we did the carbon and the oxygen, because they are in the same period, oxygen is further to the right, which means it should be more electronegative, and that should give you a polar bond without actually needing the numbers. And again, we do draw the dipole arrow, right, pointing to the side that is more negative in a polar bond, right, because of that unequal sharing of electrons. It creates a partially negative charge on one side, which is more electronegative, and a partially positive charge on the other, which is less electronegative. So this guy would have partial positive charge, partial negative charge. And as we talked about last time, again, they are partial charges because there is still some aspect of sharing happening here. The electrons haven't fully transferred. We also maybe looked at sulfur and oxygen. And once again here, they are in the same group, and sulfur is further up on the periodic table. So you wouldn't really, again, need the actual values. That should yield you a polar bond in that case. And again, it would be pointing in this case towards the oxygen. We also talked about that there is a diagonal relationship with the electronegativity values. And again, it is definitely possible to get two different elements that will share, for example, as we see here, as we also see here, and so forth, a same electronegativity value, and will give you a nonpolar bond. Again, it's sort of diagonal down to right a little bit. Again, one is further to the right, one's further up, and they sort of cancel out their differences, and they end up with actually the same electronegativity values. For sure, if you're dealing with two things in a bond that is the same element, it should obviously be a nonpolar bond because they will have the exact same electronegativity values and give you a difference of 0. Any questions on that there? All right, so then let us continue on. Again, as we talked about, ones with widely different electronegativities tend to form ionic bonds as we go kind of from the left-hand side of the periodic table to the right-hand side, and those with similar electronegativity differences will make those kind of covalent bonds. So definitely these are really what you want to look at in terms of trying to determine, what type of bond that you're dealing with, ionic or sort of covalent. All right. Now, as I mentioned maybe before, the two sort of cutoff for ionic is not perfect. You definitely, if you looked at that table, can find some ionic combinations where you will get sort of a difference less than 2. But again, if you just roll with the metal and non-metal, you'll be fine with that. We're not going to use it, and people don't use it all that often anymore, but sometimes people refer to sort of the bond in terms of percent ionic character. And percent ionic character, if it's 100% ionic character, you pretty much have an ionic bond. If it's 0% ionic character, you pretty much have a pure covalent bond. And then obviously if you're somewhere in the middle, you have, probably a polar bond that's going to happen in that particular case. So not used all that often, too much anymore. But again, a pure covalent bond is still a nonpolar bond. That's perfect sharing of electrons. Ionic, no sharing of electrons. And again, as we talked about, sort of our polar bond in the middle there, sharing electrically. Again, we can draw our arrow pointing in that direction towards the more electronegative chlorine in that particular case, as it would be more negative. That again is sometimes referred to as bond polarity. So when we talk about using a difference in electronegativity values, we're really in most cases talking about bond polarity. There is one place where we'll also deal with overall molecular polarity, but really most of the time when we do those differences in electronegativity, what we're really looking at is not necessarily the entire molecule, especially if it has more than one bond, but we're just looking between those two atoms, how those electrons are going to be shared equally. All right, so we talked about drawing Lewis structures for ionic bonding, and in those situations, we do show the electrons being transferred with our Lewis dot symbols. We do show our end result there with charges. But now we're going to talk about what we should do when we're dealing with really covalent bonding molecular compounds where everybody's kind of sharing electrons. If you follow these steps we're going to talk about, it should yield you to pretty much a pretty good structure when you draw it. If you do sort of piecework, which I'll describe maybe in a bit here as well, you probably end up with the wrong picture, not enough electrons, too many electrons, and stuff like that. So, and what I mean by piecework is what happens sometimes when people try to do this is they go, well, hydrogen's got 1, like, nitrogen's got 5, and they try to figure out kind of like an ionic bonding where all the electrons go, and that's not really a great idea because again, usually what will happen is people will end up with not the right number of bonds, too many electrons, and so forth. So when we do this sort of method here, usually will get you to the right spot. The first thing that you want to think about is how everybody's connected, and to sort of help you decide where everybody should end up. There are a few rules that you want to follow. Usually the least electronegative atom is in the center, and in a lot of cases everybody else is attached to it. There can be more than one central atom, but in a lot of cases there's just kind of one central atom and everybody else is attached to it. You should never have hydrogen or fluorine in the center. Again, for fluorine, it is the most electronegative element you could have, so it should never end up in the middle. And hydrogen, as we talked about a number of times, I think as well, should only end up with 2 electrons. So if you put it in the middle, it's going to have way too many electrons. So it should never find itself in the middle as well. Probably the most important thing you should do is count up the number of valence electrons in the compound that you're trying to draw. And remember that the valence electrons equals the group number on the periodic table. So you could, whatever the group number is on the periodic table will be the number of valence electrons. Also, if you're drawing something that's a polyatomic ion, and that is something that shares electron but still has a charge, you do have to take charges into account when you're sort of doing valence electrons. So again, if somebody has a negative charge, that means it has gained electrons, and you do need to add those electrons into your total. Again, otherwise you'll be short electrons. And if somebody has a positive charge, then you need to, in that case, subtract that from your total. So you want to make sure that you do that. So negative charge, this should actually be positive there. So they're both not negative. So if you have a positive charge, again, you need to subtract whatever that charge is from your total. Otherwise, you'll end up with too many electrons. And when we draw these pictures, that is the most important number, because when you're done drawing your picture, you do need to have exactly that many electrons in your picture, no more, no less. It's got to hit that number right on the nose there. So once you figured out kind of how it's arranged, once you figured out how many electrons you should have in your picture, the next thing that you should do is draw one single bond from the central atom to all of the outside atoms. I personally use lines to represent that. And again, you can use dots if you want to, but again, we can use lines to represent bonding electrons. So you want to draw one single bond through all the outside atoms. That each bond is going to represent 2 electrons. So each bond will represent 2 electrons and our line. And then you want to count up how many electrons you've used. You then want to subtract that from your total. And then once you do that, you then want to fill up all the outside atoms. So you'll have some outside atoms. You want to fill those up first in pairs. So you want to go around all the outside atoms, fill them up as non-bonding electrons, pairs, or dots of electrons. Once you've filled up all the outside atoms with electrons and you still have electrons left, then you should go to the center atom and add them as pairs of electrons, dots as well. At that point, you should be out of electrons if you did it correctly. A reminder that you really do not want to double bond or triple bond right out of the box. They usually will not lead you to a pretty good sort of picture. You kind of want to save that for the next step, which is once you've done that, you want to make sure that everybody has met the octet rule. And again, that is the goal of bonding, right? Is for everybody to get 8 electrons around them. That exception is, again, hydrogen. Hydrogen, again, should only have 2 electrons. It's at that point that if you use up all your electrons and you have not met the octet rule for somebody, you should try to fix that by making a double bond. And if the double bond doesn't work, then you should try to fix it by making a triple bond. So you want to kind of save your double bonding and triple bonding to kind of fix something that doesn't work. And don't want to do it right out of the gate. All right, so let's take a look at one here, which is nitrogen trifluoride. And nitrogen trifluoride, we have nitrogen, which is group number 5, which means we have 5 valence electrons for nitrogen. We have fluorine, which is group 7, and there's 3 of them. So 3 times 7 for each of the fluorines. That's going to give us 26 valence electrons. So once again, 26 valence electrons is the exact number that we need to hit on our picture. We have nitrogen and 3 fluorines. I would say in most cases, if you have one element and then like 3 of some other elements, it's the same. Probably the one is going to be in the middle. But if we look at nitrogen and fluorine, fluorine obviously is the most electronegative, should not be in the middle. So we want to put nitrogen in the middle. We want to arrange our fluorines around it. And to answer a question you might have, it does not matter. You could put the fluorine up on top or the bottom there. It doesn't really matter where you put it, whichever way you want to kind of do it. Now that I have done that, what I'm going to do is take from the central atom to each of the outside atoms 1, 1, and 1, one single bond to each of the outside atoms. Each of those single bonds represent 2 electrons, so that is a total of 6 electrons I have basically used so far off of my total. I now have 20 electrons left. Those 20 electrons are going to go on the outside atoms as dots, pairs of electrons, until they are full with 8, except unless it's hydrogen, obviously. You wouldn't put any dots. So we'll go 2, 4, 6, that should fill that one, 8, 10, 12, 14, 16, and 18 electrons there. We've now used another 18 electrons. We got 2 electrons to go. We have filled out everybody on the outside. They all have 8. Now we will go to our center atom and we will put a couple of dots there, and that will be our final 2 electrons that we need in this case. Now, what we want to check at this point is, does everybody meet the octet rule? So we're looking for 8 electrons around everybody. That is 2, 4, 6, and 8 for that. 2, 4, 6, and 8. 2, 4, 6, and 8. And 2, 4, 6, and 8. So everybody here has 8 electrons. We have a grand total of 26 electrons in our picture. And again, this would be the correct Lewis structure without all the highlighting, obviously, in this case. Yeah. Any questions on that there? So this is what I'm talking about when we talk about the electrons. We want to think of those kind of 26 electrons as not necessarily belonging to anybody, but we want to distribute them to everybody sort of as equally as we can. That's going to create sort of the good bonding and stuff that you need. Any questions on that one there? All right, why don't you try, that was what we just did. Why don't you try this one and see what you come up with? Okay, so let's take a look. So again, here we want to count up our valence electrons. So we got 5 for our nitrogen. We got 3 times 6 for our oxygens. And again, it does have a negative charge here, and that means that it has gained an electron. So we do need to add that into our total. Otherwise, again, we're going to be off in terms of our picture. That's a lot of math there, 18, 19, 24 electrons. So once again here, our picture should have 24 valence electrons. In this case, if we look at the periodic table between nitrogen and oxygen, we see oxygen is further to the right, which means it's more electronegative. So nitrogen should be in the middle here. And since it's in the middle, we will put our oxygens around it. Once again, we're going to do a single bond to each of these. At that point, that is 2, 4, and 6 electrons. So if I take my 6 off of that, I got like 18 more to go. So again, they're going to go on the outside as pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 in this case. I have now used all 24 of my electrons. Is everybody good here in terms of the octet rule? No, nitrogen is short, right? Nitrogen has only 6 electrons. Everybody else, if you sort of count it around, nitrogen's got 2, 4, and 6. Everybody else basically has 2, 4, 6, and 8 if you kind of go around it. So in this particular case, we do need to make sure that nitrogen does have 8. So can I just put some electrons on nitrogen to fix it? I cannot, because now I have 26 electrons, right? So that is too many. So we cannot do that, even though we may want to. So that's not a great idea. So this is the case, as I was talking about earlier, that we would want to try a double bond, for example, to try to fix it, or maybe a triple bond might be necessary. In this case, we will make a double bond between actually any of the oxygens in this case. They're all the same oxygen, basically. So you could actually make a double bond between any oxygen that you wish. So for example, if I wanted to, I can make a double bond right here. Can I just draw a double bond line? The answer is no, because I still now have 26 electrons, and that oxygen on top has like 10 electrons, which is too many. So when we need to make a double bond, or if we need to make even a triple bond in this particular case, or in a case, what we actually need to do is take a pair of electrons, doesn't really matter which one, and we're actually going to bring those electrons in to make the double bond. So we're going to take any pair of electrons you want. In this particular case, it doesn't really matter. When I do that, I get a no written badly, but let's make it a little bit more space there. We will end up with a double bond here. Everybody else will remain the same. And we usually put a little bracket around these guys that have charges and put the charge on the outside. And now if we count around everybody here, everybody will meet the octet rule. So this guy, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, and 8, and nitrogen 2, 4, 6, and 8 by making that double bond there. Everybody has met the octet rule. We still have only 26 electrons in this particular case. You could have, if you wanted to, not have double bonded the top. You could put your double bond over there to the right, and you would get this structure here, which would have been a perfectly fine structure. You could also, if you wanted to, not double bond to the top, not double bond to the right, but did the double bond over there on the left-hand side. And that would get you this structure here. I feel like I got an extra little dot there. Get rid of that there. Cool. And this structure here, all three of these structures would have been perfectly fine if you were asked just to draw the Lewis structure for nitrate here. You could have done any three of them. All three of them together are what are known as resonance structures. And resonance structures occur just like this, where you have basically more than one option as to where you could have done that double bond, and you could draw multiple Lewis structures. They usually are indicated by this arrows kind of heading in both directions, are resonance type structures. The reason for that is the double bond electrons in the oxygen and nitrogen, they're delocalized, which means they're really moving around from oxygen to oxygen. So at any given point, they could be at any oxygen, are in between. So the real and no one structure could really adequately describe truly what's happening in the bonding. So this sometimes occurs when you have an option like this to basically do the double bond at different spots. You could draw an equivalent sort of Lewis structure. Any questions on that there? Yeah. You could have done it on the bottom if you're asking, could you have done something where the oxygen went this way? It is, whoops, it is perfectly okay. So as long as it's connected to the center atom, you could go top or bottom. Kind of like the first one as well. You could have done the fluorine up on top versus on the bottom like we did as well. Yeah.
You said that since the lump go like to the dot is traveling around.
Yeah, there's a lot.
What instance would it be like specified to one versus like all of them?
The true version of it is it's constantly changing because of those electrons, so it's just constantly changing. So we we draw one of those three structures to indicate that it could be at any of those points, at any particular time. So that's why the true structure is probably more like this, where those electrons are just kind of traveling and stuff like that, and they're kind of constantly kind of moving around and stuff like that. So again, if you were asked a question to draw a Lewis structure for this, and that was the only question that you were asked, just draw a Lewis structure, you could lay up any one of the three pictures and they would all be correct. If you were asked to draw the Lewis structure and all the resonance structures, then technically you should draw all three of those structures to indicate that. Yeah.
But what instance would it not? Would it matter which was down double bond?
In what case would it matter where you would double bond it? It won't matter in a situation like this where you could draw a resonance structure, because that's kind of the purpose of it, is like it pretty much could go to any of those sort of options, basically. If you don't have multiple options, then you won't have resin structure. So it's possible to have a double bond without like a resin structure. But if you have like one double bond, but you could have done it at different locations, then it's possible to have sort of resin structures. Was there a question in the front or? Yeah. No, it's not. So it has to do with how many single bonds you drew to start with. So in this case, we did, whoops, if I don't lose it, we did 1, 2, and 3 single bonds. So each of those single bonds represents 2 electrons. So that's why we used up 6 electrons. Now, if I started out and I only did like 2 single bonds from the center guide to the outside, then it would only be 4 electrons and stuff. So it's dependent on how many single bonds you start with. Yeah. Other questions? And again, a reminder, each of the sort of single bond lines do represent 2 electrons. So that's again how we get up to like 2, 4, 6, and so yeah. Other questions? Okay. So why don't you draw some here just to practice? All right, let's see. Let's do why don't you draw SH2? Why don't you draw CO2? Why don't you do CO3 2 minus? Why don't you do N2? And why don't you do a little SO2? And NH4 plus. All right, so take a few moments there, draw up some nice Lewis structures for each of these, see what you come up with. And see how you're doing on these pictures. So we'll just start with the top one here. All right, so we'll go SH2. So again, we want to basically figure out our total number of valence electrons. So sulfur is group 6 up there. So that's 6. Hydrogen is 1 valence electron. There's 2. So that's for our sulfur. That's for our hydrogen. That's a grand total of 8 valence electrons. Once again, in this case, we know hydrogen should never be in the middle. So here, sulfur should be in the middle. So we'll do sulfur in the middle. Again, hydrogen on the outsides. I go left and right in this situation. You could go top and bottom. It doesn't really matter, to be truthfully honest with you. We're going to do 1 single bond and 2 single bonds. So as was an earlier question, in this case, we actually only did 2 single bonds. So that's a total of 4 electrons that we just used in this particular case. And that means that we basically got 4 electrons to go. We do not put them on hydrogen, right? Because at this point, hydrogen is done. It has 2 electrons. Remember, hydrogen only needs to get to helium to be done, right? So that is exactly, in all cases, what hydrogen should look like, pretty much. 1 line to it, and that's it. No dots, no double bonds, no triple bonds. That means that the next place that we're going to go is our center atom, and we'll put them on as pairs of electrons, so 2 and 4. That's a grand total of 8 electrons. And at this point, we should be good. The sulfur has 8 valence electrons. Each hydrogen has only 2. And that gives us a grand total there of 8. And everybody's happy. Any questions on that one there? Yeah. All right. Rolling to the next one. We're going to do a little CO2 action. So CO2, carbon is group number 4 there, and 2 oxygens each at group number 6. That's going to give us 16 valence electrons. Once again, if we look at the periodic table, we have carbon over here, oxygen over here. Oxygen is more electronegative because it's further down the period there, and that means that carbon should be in the middle in this case. It is the least electronegative. So carbon, once again, I'm just going to go side by side here. And we're going to do, once again, 1 single bond. That is 4 electrons. So again, at this point, I got 12 to go. In this case, we can't put it on the outside. So we'll go 2, 4, 6. And with the 2 originally there, that's 8. 8, 10, and 12 in this case. At this point, I have now used up all 16 of my valence electrons at this point. Is everybody good here in this case? No, the carbon is well short. It has actually only 4 basically electron pairs around it, right? It's got basically 2 and 4. Oxygen here, 2, 4, 6, 8. Guy on the left is the same, 2, 4, 6, and 8. So in this case, we do need to make a double bond to try to fix this. Doesn't matter which one we go with in this case. It doesn't, they're identical to the same. So remember that when we make a double bond, we're going to take a pair of electrons and actually move them in to do so. When I do that, that's going to give me a double bond here on the left. And now we'll have our single bond on the right. Did that fix the situation? It didn't. It made it better. Carbon is now up to 6, right? So you might be asking yourself, where do I go next? Do I triple bond? The answer is no, not at this point. Before you should go to a triple bond, you should try to exhaust all the double bond possibilities. And since we had an identical oxygen on the other side, that's another place where you could make a double bond. So the best thing to do is go single bonds first, then go double bonds and try to use up all your possible double bond options. And if that's over, then you should go to triple bond as sort of your last resort, is usually the best way to do it. So at this point, we'll do the same thing and we'll bring it in. And again, I know there's another double bond option in this case because basically it's the same element as you had on the other side. So it's basically the same idea there. And we will now double bond over here and double bond over here. And now we have something that is good because we now have 8 electrons around everybody here. And again, in this case for the carbon, 2, 4, 6, and 8 there through the double bonds on each side. Each of the oxygen, 2, 4, 6, and 8, also through the double bonding. Everybody has 8 valence electrons, and we still have used just a total of 24 electrons, which is what we want in this case. Question on that one there. Yeah. So that was maybe to answer your question earlier. Here we would double bond on both sides, and that's how we kind of know where we should do the double bonds and stuff like that. Yeah. Yes. Why could so carbon, oxygen, oxygen, and what on the one on the right? What should the oxygen look like? Dots like this. So like this, and then you have like that or something like that. Yeah. Just like that, yeah. Okay, it wouldn't work for a couple of reasons. First off, the carbon in this case would still be short, right? It has only 6 electrons. It has 2, 4, and 6, right? In this particular case, so it'll be short. So the idea here is you want to kind of follow that order that we talked about, which is basically we want to go single bond first. We then want to kind of distribute the electrons as pairs of electrons. And then at that point, you then want to go to double bond if necessary, and then kind of triple bond if necessary after that. And that will put the electrons really where they should be, because based on how the electrons should be distributed, the carbon should never get the electrons in this situation until the outside ones are filled. So we want to always kind of fill the outside ones to like the octet rule, and then kind of go to our center if we still have electrons at that point. We don't want to, again, go kind of to the center first. So we kind of want to work outside in when you're kind of distributing those electrons. Yeah. Other questions? All right, we'll go, let's do CO3 2 minus there, CO3 2 minus. So in this particular case, we got 4 for the carbon. We have 6 for the oxygen. There's 3 of them. So carbon, that's oxygen. And then obviously here we have a -2, which means it has gained electrons. So we will need to add 2 more electrons to our total. And that's 18, 20, 24 in this case again. Once again, carbon being the least electronegative will go in our center. And we will again do our connection first. So 1, 2, 3, and that is 6 electrons. So again, if you're kind of subtracting off, you got like 18 to go, I think, or something like that. So again, 2, 4, 6, that fills up that guy. 8, 10, 12 fills up that guy. 14, 16, and 18 in this case. And again, at this point, since we filled up all of our outside ones first, we actually have no more electrons to go to the center. And that's important in this case because here our carbon is short, right? It has only 6 electrons to it. So again, here we want to make a double bond. In this particular case, it doesn't matter, kind of like the nitrate one we did earlier, you could choose any of the oxygens to do so. Again, remembering to bring in those electrons to do so. And in this case, we would end up with a double bond up on top. And again, we would put a bracket and a -2 over it there to make it look all fancy. And at this point, everybody has 8 electrons, and we still have a total of 24. Once again, this is one of those ones, again, you could have done a resonance structure. You could have a double bonded to the left. Or you could have double bonded there to the right, giving you 3 resonance structures in this particular case. Just use those little arrows there and that way as well. This also demonstrates, much like the other one, that if you have to make a double bond, it doesn't mean you need to double bond everybody, right? So in this case, we don't need to double bond everybody. We just needed one to really fix the problem. Unlike the one we just did, which was CO2, where we actually did need to double bond everybody, not just for the fun of it, but we did it to, again, fix the problem that we didn't have 8 electrons. So sometimes people think if you have to double bond one, you should just double bond them all. You don't. You just need to go as far as you need to get everybody to those 8 electrons, and then you should stop. Question on this one here. Yeah.
Anything?
The brackets are typically the way when you draw anything with a charge are typically used to indicate that this has a charge. We don't talk about it in this class, but you could actually know exactly where the -2 charge is for what is referred to as formal charge, for example. The -2 actually comes from the single bonded oxygens. They each are carrying, actually in this case, based on the way they're sharing electrons unequally, they're each carrying a -1 charge, which gives that thing an overall -2 charge. This is what's known as a polyatomic ion, which is kind of a weird thing. It is an ion that has a charge, but it's actually covalently bonded. So even though it kind of looks like it is treated like an ionic sort of, it makes ionic compounds, but it itself is actually covalently bonded, sharing electrons. So those carbons and oxygens, which are nonmetals, are actually sharing electrons. They're sharing them unequally, and that's going to cause actually such an unequal sharing that kind of overall those single bond oxygens kind of take on almost like a negative charge because of that. And overall, the thing has actually an overall charge of -2. So it's kind of an interesting thing. It's like a covalently bonded thing that still has a charge, and it works as an ion as well. Any questions on that there? All right, so we'll go with, we'll do SO2 next. So SO2, this is 6 for the sulfur, 2 times 6 for the oxygens. That's 12. That's 18 valence electrons. Once again, if we look at on the periodic table, we got oxygen and sulfur. So sulfur is further up in that group. It is more electronegative. So that tells us again here, sulfur should be in the middle. And in most cases, if you just got one, that's probably the guy in the middle if it's not hydrogen. Oxygen's on the outside. We're going to do a single bond to each. So that is 2, 4 electrons. We still have some more to go there. So 2, 4, 6, 8, 10, 12 electrons. I have now put on there a grand total of 16 electrons. That's going to leave me 2 left over. And those 2 electrons actually will get here to the sulfur. And as to an earlier question, that is the way you want to distribute these. You want to go outside first, left over to the center. That's how they actually get dots there. I can't tell you how many people will draw this thing with no dots on the central atom, and it does need to have those dots there. So again, you kind of want to work outside in to do so. At this point, we want to look and see if everybody's good, and hopefully you can see Sulfur is not so good. That is 2, 4, and 6 electrons. So it is short. So once again, in this case, you can make a double bond at either of these oxygens. I'm going to bring it in here on the left, and that will give me a double bonded oxygen on the left, still a single bond on the right, and that sulfur still needs those dots on it to be correct. Yeah, so again, by those distributing those electrons sort of properly at the beginning, that puts those dots that should be there. You could also draw on a resonance structure for this guy, a little double bond here to the right, as opposed to the left. And again, this is the proper structure. It is not double bonded on both sides with no dots on the on the sulfur. It does need to have only one single bond and those two dots being present. Question on that there. Okay, then what we got next there, we'll go NH4 plus next. So we got 5 for the nitrogen, 4 for the hydrogen, 4 times 1 for the hydrogen. And this has a plus sign, which means we need to subtract off there 1. So that's going to give us 9 minus 1 is 8 valence electrons. In this case, we know hydrogen should never be in the middle. So that's going to be a nitrogen, some hydrogen happening here. So we're going to do a single bond to each of these. At that point, that is 2, 4, 6, 8. Looks like a winner. A little bracket over that and so forth, and we're good. Again, here, nitrogen has 8. Each hydrogen has 2, which again is the maximum it should have. And again, that is exactly how hydrogen should always look, just like that, pretty much. Yeah. Any questions on that there? And lastly, we have our friend nitrogen, a little N2 action. So that is 2 times 5. That is 10 valence electrons. In this case, there really is no central atom. So in this case, you could just really put the two guys side by side. And you could also just follow the same steps that we did before, even though there's only 2. So the same steps would be, I'm just going to connect with a single bond. That's 2 electrons. That gives me 8 to go. Going to do the same thing. I'm just going to start on one of these guys and put some electrons down. So 2, 4, 6, and 8. I have now basically put on there my 10 electrons. And you can see at this point, the nitrogen on the right is actually good, but the nitrogen on the left is not good. It has only 4 electrons. So here we're going to go with our double bond, right? So we're going to take a pair of electrons and bring it in to make our double bond. That would give us something that looks like this, double bonded. Did that fix the problem in this case for our nitrogen on the left? It did not. It got us closer. We now have 6 on the left and 8 on the right. At this point, there is no other place we can make a double bond. So now we need to go to the next step, which is a triple bond. So we do triple bond the exact same way we do double bond. We're going to take a pair of electrons and bring it in to do so. And when we do that, a little nitrogen triple bonded action, which is how nitrogen gets to a triple bond, basically in that case. By triple bonding in this case, that allows each of the nitrogens, once again, to get to those 8 valence electrons and be really stable in that case. Any questions on any of those type of things? Now, most of the stuff I'd say you probably would draw will have one central atom. It is possible that you could have something, for example, that has 2 central atoms. So for example, let's say we did nitric acid, which is actually HNO3, and we wanted to draw the structure here for nitric acid. Hydrogen is 1, nitrogen is 5, there's 3 oxygens, each at 6. That's 18, 19, 24 valence electrons in this case. Now, in this case, because it's actually an acid, it is actually set up similar to what you would expect, perhaps. We have a nitrogen in the middle. We have our 3 oxygens. But the hydrogen here is actually not connected to the nitrogen. It's actually connected to one of the oxygens in this particular case. And that's what makes it an actual acid. And if it was something like this that I did not think you knew sort of the structure, I would obviously tell you kind of how it's put together. but in this case, the hydrogen does not end up on the nitrogen. So in this case, how would we make the Lewis structure? We would actually just continue to follow our same sort of process. We would do a single bond to everybody. So we're just going to single bond up everybody in this case. And that's going to give us 2, 4, 6, 8 electrons, basically. So now we put up there 8 electrons, a lot of mass, 16 electrons basically to go. The next thing we're going to do is exactly the same thing we did when we had one central atom, which is we're going to work outside in. So should I put dots on my hydrogen? No, we should never put dots on hydrogen. Then you get the unhappy face in the X. You don't want that. So nothing on the hydrogen, but we can put dots here. So 2, 4, 6, 8, 10, and 12. So we put 2, 4, 6, 8, 10, 12. We still got 4 more electrons to go basically at this point. The next sort of outside one is the other oxygen there. And at this point, it already has 2 bonds, which is 4 electrons. So it could take 2 and 4, and now we're at 0. At this point, we have now put on there basically all of our 24 electrons in this case. Is everybody good in this case? No, the nitrogen is actually short. The nitrogen has 2, 4, and 6 electrons in this case. So what do we do here? We do the exact same thing that we did before. We can make a double bond. This case, you probably would not want to make a double bond to this oxygen. And that's because it's got kind of like the hydrogen hanging off of it. But you could double bond this oxygen since it's by itself. You could also double bond this oxygen because it's by itself. And that, I think, maybe as to your earlier question as well, how do you choose maybe which one to do or when you shouldn't? This would be a case really you probably wouldn't, in most cases, do the double bond to the guy with the OH. As I mentioned before, this is actually what makes it an acid. It's this hydrogen pops off basically is what kind of makes it an acid. So we would probably only double bond either the top guy or the bottom guy. We would do the same thing. We would take those electrons and bring it in. And if we do that, that would make our double bond up on top. We would still have our single bonded oxygen here, also our single bonded oxygen here. And now we would have, once again, 24 electrons. Everybody again would have 8 electrons around except for hydrogen that's 2. By the way, because I do have that option of I could have double bonded to the guy on the left, I could also draw a resonance structure for nitric acid where the double bond is actually over here rather than up on top. And we would end up with something like this as a possible nether structure. Again, in most cases, you probably want to play with the OH part. So I would say, again, when we talk about all the possibilities, for example, for resonance structures, what you're looking at is, if you could double bond to this element, is there another one that looks exactly somewhere else that you could have moved the double bond to? And that's how you could kind of choose, in most cases, the correct way to kind of do it. Question on drawing Lewis structures. So again, if you kind of follow these steps, it should lead you to a pretty good structure at the end. I won't say maybe always the best structure, but in most cases, it will lead you to a pretty good Lewis structure. We don't get into better structures versus worse structures. You get into that in 1A, but there is a way, kind of that formal charge thing I talked about just a second ago. You could calculate what's known as the formal charge for different structures and choose one that is better than another based on that. Yes. Well, hydrogen can be attached to something in the center, but it cannot be in the center itself. So you cannot have hydrogen as like the central atom, like, kind of like this deal or something like that. That's a no-no because hydrogen is going to have too many electrons. But you can have hydrogen attached to something in the center like we have here. That's perfectly fine. It just happens in this case because this is actually an acid. What makes it an acid is actually that bond right there. And that's what allows it basically to kind of go off and release that hydrogen. So that's how we kind of know in this situation that the hydrogen is actually attached to the oxygen rather than the nitrogen in this case. Because it's an acid, yeah. So usually most acids that have oxygen have that bond, that OH bond. And the reason for that actually relates to what we were talking about with electronegativity. this is a polar bond here, right? The difference in electronegativity between oxygen and hydrogen will make the oxygen more negative, the hydrogen more positive here, because they're not sharing electrons equally between them. And that actually weakens the bond if you think about it, because the electrons are actually heading towards the oxygen. This hydrogen is just barely hanging on, and that's why it's able to drop off pretty easily. It's also why it's a strong acid, because it's able to pop off relatively easy in solution and stuff like that. So it's just for that reason in this particular case. And again, in this class, I wouldn't necessarily expect you to know that. And if I gave you something like that, I would show you. I'll give you kind of the structure, something like this, or I'd tell you in words like the hydrogens attached to one of the oxygens or something like that. Yeah. Other questions on that? Yeah. All right, so you do need to be able to obviously draw Lewis structures. So now that we did that there, we talked a little bit about resonance structures, but a couple other things about bonds that's important. Bond length. So the length of the bond actually gets shorter every time you put on another bond. So if we just look at a comparison, you don't need to memorize these numbers at all, but if we look at carbon-carbon single bond, double bond, and triple bond, single bond's about 154 picometers, double bond 133, triple 120. So what happens is, as you make that bond with those electrons between the two atoms, everybody gets pulled in tighter to each other. So the outside atom, as they're making the double bonds, gets closer to each other, and the distance between them gets smaller. Same thing, carbon, nitrogen, single, double, and triple. We see the size start to decrease as time goes on, as you make more and more bonds. So in general, a single bond is longer than a double bond, and a double bond is longer than a triple bond. It's not like twice as long if a double bond for a single bond, or or 3 times as long. But that's sort of the trend. Single bond is your longest bond. As you pull those electrons in to make the double bond, everybody comes closer. As you pull them in to make a triple bond, everybody comes even closer. That also relates to bond strength. So typically speaking, a triple bond is stronger than a double bond, and that is stronger than a single bond. I usually think about that like a pencil, right? If you grabbed a brand new pencil right out of the box, never been sharpened, you could snap that thing pretty easy, right? If you take like a chemistry exam or something, you're left with like an eraser and a nubbin of a pencil like that big, super hard to try to break it, right? Because everything's just too close together. And that's sort of what happens, right? As these electrons go between the atoms, everything just kind of centralizes and brings everybody closer together, makes it harder to break. So again, a triple bond is not like 3 times as strong as a single bond or anything like that, but that is the general trend that occurs. As I mentioned before, resonance structures are often used when we do have multiple locations as to where we could put that double bond. And again, you could draw different resonance structures wherever you basically have the option to kind of move the double bond around to this similar or same sort of atom that's in the structure. So again, ozone is an example of that. You don't have to worry about the charging on that, but ozone actually has, you could double bond over here. You could also double bond it on the other side. Again, that creates a resonance structure. Carbonate, as we saw earlier, and benzene ring, if you take organic, will look something like this. It's actually a 6-carbon ring where each of these kind of points are carbons and hydrogens attached. Actually, 1 hydrogen attached at each of these. And it actually has, although nobody ever draws them out in this thing, it has actually 3 double bonds in it. And you could draw a resonance structure where those double bonds are over here. And sometimes in some books, maybe not a real chemistry, organic chemistry book, but sometimes they will show this benzene ring with like a circle in the middle. And that indicates that those double bond electrons, as we've been talking about, can be moving around from kind of carbon to carbon. So that's very common sometimes for benzene. I would say if you're taking real organic, like you guys probably will, you probably draw it with actually the lines like that. But sometimes in, let's say like baby organic or like organic that's taught sometimes in like health majors, chemistry and stuff like that, they'll kind of use this circle in there. So, but sometimes in real organic, they'll use it, but not a lot of times and stuff like that. Yeah. Question on that there. All right, and then here you can obviously have many, many options. If you've got multiple double bonds happening in this particular case. So let's just talk about a few of the exceptions to the octet rule and what's going on. So there are a few exceptions that could happen to the octet rule, although in this particular class, we will always follow the octet rule. So everything in here should always follow the octet rule. But in reality, and when you take 1A, you'll do nothing but like a lot of exceptions. But here, we're just going to assume everything will follow the octet rule. One exception, though, to the octet rule is an incomplete octet. And an incomplete octet, much like the name implies, has less than 8 electrons. And boron and aluminum to an extent, or beryllium are examples of that. But most of the time, boron's going to be your winner. It is perfectly okay with less than 8 electrons. Actually, it goes 6. It is something what is referred to as being electron deficient because it has less than 8 electrons. But I would say boron in most cases is probably the element that you would see the most. Technically, beryllium and aluminum can do that, but usually they're more ionic sort of compounds. So, sort of covalent bonding. Boron usually is the one that you see. Another exception to the octet rule is an odd number of electrons. And that is basically when you end up with one unpaired electron. So if you take something like NO and you do all the Lewis structuring that we do, you'll actually end up with one unpaired electron. Those are sometimes also referred to, for example, as free radicals when they talk about that. A lot of that happens up in atmospheric chemistry with chlorine. It makes them usually fairly reactive because it has one electron. It doesn't really like that. Yeah, so it wants to kind of fix that situation. So they're usually very, very reactive. Probably the exception to the octet rule that you will come across the most in your chemistry career, especially when you get to 1A, is the expanded octet. And the expanded octet, much like it sounds, is something could actually go over 8 electrons. You could have something that has 10 electrons or 12 electrons over it, and it is perfectly okay. That happens when you look at the periodic table where our friend sulfur is. You look to the right, to the left, and down. Anybody there can technically go over the octet rule and have this expanded octet. That is because when we look at sulfur, it's on what period on the periodic table? Sulfur is on period number 3. And that is equal to N is equal to 3. When we did electron configurations, what orbitals begin on the 3rd energy level? Bless you. On the 3rd energy level, that is where you start to see your d orbitals. So because they have d orbitals available to them, even though they may not be using them, they have a place to stash the extra electrons. So they could actually go over, like I said, upwards of like 12 electrons they could like pile in there. That is also why, though, if you go less than sulfur on the periodic table, where we have like nitrogen, oxygen, those guys, that is period 2 on the periodic table. That is N equals 2. There are no d orbitals on the 2nd energy level, which means they can never, ever go over 8. And that's why we take sulfur basically right, left, and down, non-metal sort of area. Those are the ones that have the ability to do so. With that being said, you should not do it in this class because everything will be a octet rule. But this is also why when you Google something, you may actually see sulfur a lot of times. For example, looking at something like this. And it actually has 2, 4, 6, 8, 10, 12 electrons around it. And it's actually good. Here's sulfur. I won't draw all the electrons on the fluorine, but all those fluorines have electrons around them. And if we just look at the relationship between fluorine and not drawing too many there, we'll get rid of one. We have 2, 4, 6, 8, 10, and 12 as well. And that's a very common thing. When you draw something like sulfate in this class, you should actually end up perhaps with it all single bonded. And it's perfectly fine because it has 8 electrons on everybody. Everybody meets the octet rule. If you look, like I said, online, you will sometimes see sulfate like I drew it there. Get rid of that there. You will sometimes see sulfate drawn like I scribbled earlier, like this. And this is also fine. And believe it or not, in this situation, this is actually better structure than this one based on formal charge, but we don't talk about that here. So that's why you do see that it does have the ability to do so. But for us, you should draw the one on the left so your teacher doesn't think you just Googled it, right? And you actually follow the way we were talking about here. Any questions on that there? Okay, we'll lay it up there. Today we have a